Okay, so we've talked about ionic compounds. The next category is molecular compounds. So, reminder, molecular compounds contain nonmetals. And these form covalent bonds. They do not form ions, and so there are no ionic charges. We can have several compounds between the same two elements. So, as examples here, all of these compounds form between nitrogen and oxygen. There's 6 of them. So if we're looking for the compound that forms between nitrogen and oxygen, there's not just one, there's a whole bunch of them. And so we need a naming system that is going to give a unique name to each of these compounds. So again, molecular compounds are nonmetals only. And the ones that we're going to learn to name have 2 nonmetals. There are compounds that have more than that. We're not going to have to name them. Okay, save that for another class. 2 nonmetals, so we call these binary molecular compounds. And we're going to use those same prefixes that we used for the hydrates. Okay, so I'm going to tell you, the molecular compounds are the ones that students find the easiest, and it makes a lot of sense to you, and you really like it, and then you try to apply this system to everything else. You can only do it if you have 2 nonmetals. Okay, you can't do this for ionic compounds.
So there's binary ionic compounds as well.
There are binary ionic compounds, but you can't use these prefixes. Yes?
When you say molecular compounds, isn't it the same covalent bonds, or are those 2 separate things?
Molecular compounds have covalent bonds.
Right.
And so you could call them covalent compounds. Yeah.
Okay. So it is.
Yeah, so they really are the same thing. I won't really test you on this at all, but just so you know, why does one element always come first? Why does the nitrogen come first and then the oxygen? Why don't you write it the other way around? We write the more metal-like element first. Generally, it'll be the element with the smallest group number. That's just sort of explanation. I'm not going to test you on that. So we use these prefixes to tell how many atoms of each element are in the compound. So here's the pattern. We've got a numerical prefix in the name of the first element, and that first element is sort of pretending to be the metal. And so it doesn't change the ending of the name or anything, just the element name. And then we have a numerical prefix and the second element's name, but this one is acting like the anion in an ionic compound, so she changes the ending of her name to "ide." Yes?
If they're in the same group, how do you know which one gets written?
That's a good question. If they're in the same group, how do you know which one goes first? Well, there's a trend for metallic character, and it's actually like the easiest trend there is. So like if you look at group 5A, we see that nitrogen's at the top, it's a nonmetal, and bismuth is at the bottom, and it's a metal. So as we go down, they're becoming more metallic. As we're going across from right to left, they're becoming more metallic. So you can just look at the position on the periodic table, which one is physically closer on the periodic table to the metals. And that's basically how it works. Again, with the number 1, for the first element, if there's only one, we omit the prefix mono. Not sure exactly why, but we would end up with an awful lot of compounds named mono something. So then you get the Merck index and the alphabetical listing, and the M's would be huge. Maybe that's why, maybe not. So an example here, NO2. So the first element is nitrogen, and there's only one. So on that first element, we omit mono. So there's nitrogen. And then the second one, there's 2 of them. So di, and oxygen becomes oxide. Okay? Now, these 2 you need to be aware of. Ammonia and water. Oops. This would be dihydrogen monoxide and nitrogen trihydride, but they never use those names. Everyone always uses their common names, water and ammonia. So you need to know that the formula for water is H2O and the formula for ammonia is NH3. There are common names and older system names for a lot of the other compounds. The only ones that you need to learn, though, are the systematic names. There's nitrous oxide and all these different ones. So let's look at a couple of examples. Let's name this one N2O5. So before you break out the prefixes, look at the first element. Is it a metal? No. Okay, we can use prefixes. Because if it was a metal, we have to do the ionic thing. So how many nitrogens? Two. So it's di-nitrogen. And how many of the oxygens? 5. Penta, right? Penta, and then oxygen becomes oxide. Dinitrogen pentaoxide. Now, we've got a double vowel thing going on in there. Sometimes the last vowel on the numerical prefix gets dropped and sometimes it doesn't. So if you're handwriting answers, I will accept either. If it's multiple choice, I will not try to trick you. Okay? Write the formula for phosphorus tribromide. What's the symbol for phosphorus? P. How many phosphorus atoms are there? Just one, because it doesn't say anything else. Tribromide means 3 bromines, so Br3. Any questions? Yes?
When do you use
Mono is used when there's one element of the second element, one atom of the second element. We just leave it off on the first one.
Could you use an example of that?
Well, this is an example where the mono's left off. So instead of monophosphorus tribromide, we drop the mono. If you have something where there's only one of the second element, like CO, the first element is carbon, and then there's one oxygen. So this is a place where we drop the extra vowel, because that looks weird, doesn't it? Monoxide? Monoxide. But if you wrote monooxide, I'd count it correct. I don't think that's a detail worth stressing about, especially since there's some of them like pentaoxide. I see pentaoxide and pentoxide. I've seen it both ways. And there doesn't seem to be general agreement on when to drop it and when not to. Any other questions? So acids. Acids are actually molecular compounds, but they're special. So acids can be defined in several different ways. The definition we're going to look at right now is that acids are molecular compounds that release hydrogen ions when dissolved in water. So an acid has to have hydrogen in its formula, and that hydrogen is written first. So for our purposes, if you see a formula that starts with H, you can assume it's an acid. Okay? So HCl is a molecular compound. It's actually a gas in its pure form, but when you dissolve it in water, it forms hydrogen ions and chloride ions. So H plus AQ. That AQ means aqueous dissolved in water. So for the most part, when we write the formula for an acid, it really should have AQ afterwards because, for example, this HCl gas would be named as a molecular compound, and HCl aqueous would be named as an acid. This is another thing. I'm not going to try to trick you on this, but you'll see most of the acid formulas have AQ afterwards, and that's why. We're treating this as the acid, not as its pure compound. If a compound has hydrogen in it, but it doesn't dissolve in water, it doesn't produce hydrogen ions, and then it's not an acid. So, characteristics of acids, they taste sour. And if you guys like Sour Patch Kids, or sour candy, I think that's nasty, but my kids just love it. They stick it in their mouth, they screw it all up, their face up, and all. Do you know why it tastes sour? Because it's covered in acid. What? There's drugs in Sour Patch Kids? No, not that kind of acid. Just like regular acid, like lemon juice acid. It's not dangerous in the amounts that are on there, but it does taste very sour. Lemons taste sour, right? Citric acid. Okay. Another characteristic of acids is they can dissolve many metals, like zinc, iron, magnesium, but they don't dissolve all metals. So remember the experiment we did on Monday. That's the day it was. It was Monday. You took the copper wire and you added nitric acid, and the copper wire melted. It disappeared, right? It dissolved. The acid dissolved the metal. Here's a photograph of hydrochloric acid dissolving zinc metal. Okay. We recognize acids because their formulas start with H. So again, when we're identifying a naming system to use, we're going to look at the first element. Is it a metal? If it is, use ionic. If it's not a metal, well, is it hydrogen? If it's not hydrogen, then you're on the molecular group. If it's hydrogen, it's a special part of molecular, it's an acid. Okay? Two types of acids: binary acids and oxyacids. So the oxyacids, as their name suggests, these contain oxygen. I don't really like this other category because I can think of one example that falls in the category that doesn't have just two elements. So I think of them as the oxyacids and the other ones. Okay? And there's a different pattern of naming. So for those binary, those other acids, naming other acids, no oxygen. We use the prefix hydro, so that represents the hydrogen at the beginning. And then you take the rest of it, if it's HCl, you take the Cl is chlorine. You take the base name of that element and you change the ending to ic, and then you put the word acid on the end. So this is if there's no oxygen. Examples. So name the acid HF. Yeah, so this is not oxygen. So we use hydro for the hydrogen. Hydro, fluorine becomes fluoric acid. Okay. I just like to point out the spelling of fluorine. The U comes first. Common misspelling is like this. Fluorine. Fluorine is gluten-free. There's no flour in fluorine. Okay, that's wrong. Write the formula for hydrosulfuric acid. The prefix hydro in the front tells me there's no oxygen in this. It's probably two elements. When acids dissolve in water, they form ions. And so we can use the ions that they form to help us figure out what the formula of the acid is. So hydrosulfuric, we're going to have hydrogen ions and sulfur ions. What charge do sulfur ions have? 2 minus. How do we know that hydrogen ions have a +1 charge? That's why hydrogen's hanging out in group 1, even though it's not a nonmetal. I mean, it's not a metal. It's not a metal. Okay, so we've got H plus and S2 minus. How do we write a formula that's neutral? H2S. And then, to be safe, we really should put AQ. Because H2S, AQ, is hydrosulfuric acid. H2 gas is dihydrogen sulfide. A very, very stinky gas. Any questions? Yes?
What does the AQ stand for again?
AQ stands for aqueous, dissolved in water. It's a little bit like the Spanish word agua, except you turn the G backwards. Aqua. Any other questions?
Would you ever have a compound starting with H that isn't able to be dissolved in water?
Yes. The question is, would you ever have a compound that starts with H that's not able to be dissolved in water? Yes, that certainly can happen. I can't imagine it happening in this class, though.
So you can assume it's an acid.
Yeah, if it starts with H in here, you can assume it's an acid. Yep.
And it's a molecular compound will dissolve in water and forms ionic.
Right. Acids are molecular compounds. Because you look at this and it's 2 nonmetals, right? That's molecular. It's not ionic. But when you put it in water, it forms ions. And that's what makes them special, is it forms the hydrogen ion. It's the hydrogen ion that makes it an acid. Okay, oxyacids. These have oxygen in them. They still start with hydrogen, but there's going to be oxygen in them, so they're very easy to recognize. These are named from the name of the oxyanion. So again, we need those polyatomic names. So we identify we cover up the hydrogen and say, well, what's the name of the rest of that? It's from that table that you're supposed to memorize. All those oxyanions ended either in ate or in ite. There was sulfite and sulfate. There's hypochlorite. There's perchlorate. They all end in ate or ite. So we change the ending of the ion's name. If it's ate, pointer. If it ends in ate, we change it to ick. If it ends in ite, we change it to us and put the word acid. So as with several things in chemistry, we have 2 things, ate and ite, and we have ick and us, and we have to figure out how they go together. So easy to get them backwards. So I'm always looking for tricks. So I'll give you 2 sentences. Rick ate him before he could bite us. Oops. So here we have ick and ate, ite, and us. Another one that a lot of people use is the white mouse ate icky cheese. White mouse ate icky cheese. So there's ick and ate. There's ite and us. I guess it should be the. Okay? So we need to be able to pair those up reliably. Okay, so let's name this one. So obviously, from the title here, we're naming oxyacids, but let's pretend we didn't see that. And we look at this compound, HNO2, we see it starts with an H. That should make us think acid, right? And the AQ, definitely acid. So here's H, and then does this have oxygen in it? Well, yes. Yes, it does. So what we're going to do is cover up the H. What do we have there? We have NO2. Well, write the formula for that. NO2 minus. If you can't remember the charge, this is a 1-to-1 hydrogen to that ratio, and so it must be 1 minus, right? What's the name of this? This is the nitrite ion. Yeah, that didn't go very well. Nitrite. Okay. So we take the ite ending and change it to us, and so this is nitrous acid. No hydro in front. Questions? Write the formula for perchloric acid. So the word acid tells us very clearly this is an acid, right? It's just right there. It says it. We look at what the word before acid, perchloric. It does not start with hydro, right? So that tells me this is an oxyacid. So perchloric, I want to change that ic. What goes with ic? 8. So this is from perchlorate ion. So I'm going to write the formula for the perchlorate ion. And I've got hydrogen ions. And then I will use the charges of those to figure out how to put them together. So the perchlorate is a -1 charge. I only need 1 hydrogen then. So HClO4, and then best to put AQ in parentheses. Any questions? I already did an example of this, but here's the written instructions. To write the formula, when the name ends in acid, the formula starts with H. You write the formula as if it were an ionic compound, even though it is molecular, because it forms ions in water. If you've got a hydro prefix, it means it's a binary acid. If there's no prefix, it means it's an oxyacid. For the oxyacids, you look at the ending of that first word. If it's ic, the polyatomic ion ends in 8. If it's us, it ends in ite. You write the formula for that, and then you figure out how many hydrogens need to be with it. Okay. Here's a couple of extra examples. Write the formulas. Yeah, question? Mm-hmm. So when it says no prefix, what it means is it doesn't have the hydro prefix.
Okay, so per, right? So like on the left.
So if it has per, then that's part of the ion name. We're looking for hydro for the acid. Here, no prefix, no hydro prefix means it's an oxyacid. Does that answer your question? Not really?
Going back to the previous example. For perchloric acid,
Mhm.
like, what if I was given HClO4, like, how do I know to use per?
Okay, that's a good question. So if we were doing this the opposite way, and I'm trying to name HClO4 aqueous, well, I cover up the hydrogen, and what's left is ClO4 minus. I need to know the name of that ion, which you memorize. Okay, so quick review of the oxyacids. The way I like to think of them is there's chlorate. So if we have,
So I know there's hypo and then there's hyper.
yeah, so ClO4 is chlorate with more oxygen. So this is the perchlorate. Okay? No. There's hypochlorite, but ClO2 minus is chlorite, the light version. And ClO minus is hypochlorite. Okay. And it takes a little practice. And I know all of those names are very similar to each other, and the formulas are very close, but there is a pattern that's used consistently. And the alternative to this, the older naming system, hydrochloric acid was muriatic acid. So there's no clue in the name what that's from, and you have all these different names. I mean, it's like Joe and Susie and Sam and Betsy. How do I remember which one is which? So that wasn't a very good system. So we have this system, and we have to be really precise with it, but it's consistent, and so we learn the system, and then we can name a whole bunch of things, right? And we make mistakes, and we fix them, and we learn, and we go on. So let's do this right formulas. Hydrocyanic acid. Well, obviously it's an acid. What does this part tell me? It's the binary acid. No oxygen. So I'm going to look at the rest of this, cyanic, for the other element. Cyanide. Yeah, cyanide is Cn -1. Why? Because I told you to memorize it. Yeah, cyanide. And then hydro, this being an acid, there's an H+. And so from the charges, I see that when I put these together, I get HCnAQ. This is why I don't like to call them binary acids. Does that have 2 elements in it? No, it's got 3. But it's named as a binary acid. So I prefer to think of it as oxyacids and the other kind. There's no oxygen here, other kind. Any questions about that one? Phosphoric acid. Is this oxyacid or other kind? This is an oxyacid because it doesn't have the hydro prefix. So an oxyacid, I'm going to look at this ic ending and change it to 8. So this comes from phosphate, or it has phosphate in it. And again, that OR in phosphorus kind of comes and goes, and we just have to be okay with it. So it's not phosphorate, it's phosphate. So what's the formula for phosphate? PO4 3-, because we memorize it. And then I'm going to need hydrogen ions with that. How many hydrogen ions? 3. So this is H3PO4 aqueous. Any questions? Now this one will mess with you a little bit. Hypochlorous acid. Oxyacid or other? It's an oxyacid. So hypo looks a lot like hydro, right? But it's not the same. It's not hydro. So this is also an oxyacid. I change us to ite. Yeah. It's hard to remember. The white mouse. Whoops. Just got an extra bit of space in there. This is from the hypochlorite ion. So the way I think of it, I memorize chlorate is ClO3 minus. Chlorite is one less oxygen. Hypo is one less than that. So hypochlorite ion is ClO minus. And then I'm going to have a hydrogen ion. I've got a positive one and a negative one. I just put them together. HClO, AQ. Any questions?